Hello everyone. So hopefully this is going to be a brief and video in this series where so I'm actually just going to walk you through an example of an optimization problem where we look at maximum and minimum points that are not just in, we look at interior maximum minimum as well as border solutions. So let's go ahead and see how that works. Okay, so we're told so we have this example where we have a monopolist who faces this particular demand function. X is equal to 100 minus P, where X is the output and P is price. And we have a total cost function, C of X, which is given to us. And we want to find output X star that maximizes profits, and we want to find the maximum profit at this particular point. So this looks like a fairly straightforward problem, and we know how to find critical points and points of maximum here. Let's go ahead and start with the usual way of analyzing our critical points. So this first step is to actually compute the profit function, which I told you that economists typically use the notation pi of x to refer to profits. So profits are actually revenue minus costs. So we have the revenue function that comes from P times X. We're given X here, so we can write the function P in terms of X. So we get 100 minus X, which is P, and into X. So that's my total revenue function. And I have my cost function given to me. So profits are actually just revenue minus costs. So, and I end up getting the profit function that looks like this. I would encourage you to solve and work through this problem on your own, but this is just a really quick example that shows us all that we need to know, tying in together the interior and border solution. So, but yes, please do work through this example on your own as well. So I have a profit function here. Now remember that we want to find output X star that maximizes profits. So one way of thinking about it is that output can never be negative. So you're actually maximizing profits subject to the constraint that X can never be negative, that is X is greater than or equal to 0. So the objective or our goal here is to maximize this profit function subject to this constraint. So what's the way to do it? We start by doing the usual first order conditions where the first derivative is equated to 0, and we find that first derivative is 0 at X is equal to 1 or at X is equal to 1. Now to know which of these are maximum and minimum points, we look at the second derivative, and that happens to be minus 2x plus 12. And we evaluate the second derivative at each of these X values at X is equal to 1. And what do we find? At X is equal to 1, the second derivative is actually positive. Therefore, we're looking at the local minimum. At X is equal to 11, the second derivative is negative. Therefore, we're looking at the local maximum. So far so good. This is something that we've been doing in the first and second derivative tests, and then I've just applied the same logic. And now what I'm doing is I'm actually going ahead and computing the profit values for each of these X values. And at X is equal to 1, we know we have a minimum, and we see that profit is actually negative. At X is equal to 11, we know we have a maximum, and the maximum value of profit is given by 334.3. So we've actually done what the question has asked us to do. And we've looked for interior solutions. But remember, when you are maximizing a function subject to a non-negativity constraint like this, you could also have solutions on the border. That is, you could have solutions where X is equal to 0, and that point would be a maximum. Now, how do we know if X is equal to 0 actually gives us a maximum point? Well, you have to look at the slope of the function at X is equal to 0. So we have not checked the value of pi of X at the local maximum points, but is that the only one? We have to check for boundary solutions. So we look at the sign of pi prime of X, which is the first derivative, at the border, and we check if pi prime of X is greater than 0 or less than 0. So this is equivalent to look for the sign of f prime of 0. Now, and instead of f prime, we have pi prime. And how do I find pi prime of 0? Well, this is just pi prime of x. In place of x, all I'm going to do is just plug in the value x is equal to 0. And when I do that, I find that the slope at point 0 is minus 11, and therefore it is negative. So we actually have a boundary local maximum at this point, x is equal to 0. Now, is that the global maximum? Which one results in higher profits? Is it x is equal to 0 or is it x is equal to 11? So to do that, you compare pi of 11 and pi of 0. And you find that pi of 11 is 334 by 3. And pi of 0 is actually minus 15. How do I compute these maximum profit values? I plug in these x values into my original profit function, and that tells me the corresponding profit values. Now, we know that we have two local maximum points. One is an interior point, which is at x is equal to 11, and we have an exterior, we have a boundary solution at x is equal to 0. We have two maxima, two local maxima. Which one gives us the higher profits? Naturally, x is equal to 11, giving higher profits. And another way you might want to think about the economic sense here is that when you're producing nothing, when x is 0, you're not actually making profits. So pi is equal to 0 cannot be giving you more profits than pi is equal to 11. So, of course, in most circumstances, I would expect that this would hold true. Anyway, you go ahead and check, and you see that it's more profitable. The more profitable of the two options is that x is equal to 11. And therefore, profit maximizing output is x is equal to 11, and the corresponding profit value is actually 334 by 3. Now, what I've done is I've picked up two local maximum points, and I've told you which one gives a higher profit. But is that the same as finding the global maximum? The only way to know that is to actually sketch the function and try and understand the behavior of the function. Now, for that, I'm just going to quickly switch to Desmos, and let's plot the function. So we have a profit function that is, say, minus 1 by 3x cubed plus 6x squared, 6x squared minus 11x minus 50. Okay, so that function looks very interesting. Remember that we are only looking at non-negative values of x, and Desmos actually allows you to do this beautifully. All that I have to do is I want to put my function in curly brackets, and I will just put in the extra condition that I want to plot this function such that x is greater than or equal to 0. And once I type the function in this manner, Desmos is only going to show me the plot of the function for positive values, or sorry, for non-negative values of x. So this particular function is what we are interested in focusing on. Now, let me draw your attention to these three particular points here. So we definitely appear to have a global maximum when x is equal to 11, right? Because the function, when you actually look at it, doesn't seem to go higher beyond this point. So that definitely appears to be a global maximum. Now, what's happening at the other 2 points? So we had a critical point there, and that was when x is equal to 1, I think. And that's a minimum point. That's a local minimum point. It's not global because the function takes on lower values than that at other points. So that's a local minimum. Now look at what's happening at the point 0, 50. Well, you can see that that's actually a local maximum point, right? Because the function definitely dips after that and then climbs back again. So there is a border local maximum there. And you can also see that the function is negatively sloped at that point. So this tallies with how your pi prime of 0 is negative. And so this is a graphical confirmation that We have identified the local maximum and the local minimum points correctly. And we have actually found that profit is maximized when x is 11. And from the visual appearance of the graph, it does look like that happens to be the local maximum. So I will stop this lesson right here. And so we have now reviewed local and global optima. We have also gone through the idea of how we can have border solutions. So hopefully that gives you a good sense of optimization of single variable in functions of single variables. So good luck, and I will see you in the next lesson.